The paper of the day is Attention is All You Need. The dominant sequence transduction models are based on complex recurrent or convolutional neural networks that include an encoder and a decoder. The best performing model also connect the encoder and decoder through an attention mechanisms. They propose a simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. Experiments on two machine translation tasks showed these models to be superior in quality while being more parallelizable and requiring significantly less time to train. Author's model achieves 28.4 BLU on the WMT 2014 English to German translation task, improving over the existing best results, including ensembles, by over 2 BLU. On the WMT 2014 English to French translation task, the model establishes a new single model state of the art BLU score of 41.8 after training for 3.5 days on 8 GPUs, a small fraction of the training cost of the best models from the literature. Authors show that the transformer generalizes well to other tasks by applying it successfully to English constituency, parsing both the large and limited training data. So here's the model architecture that is presented in the paper. There is encoder. The encoder is composed of 6 identical layers. Each layer has 2 sublayers. The first is multi-head self-attention mechanism, and the second is a simple position-wise fully connected feed-forward network. They employ a residual connection around each of the 2 sublayers, followed by a layer normalization. That is, output of each sublayer is layer norm, that is x plus sublayer x, where sublayer x is the function implemented by the sublayer itself. To facilitate these residual connections, all sublayers in the model as well as the embedding layers produce outputs of dimension d model equal to 512. Then there is a decoder. The decoder is also composed of 6 identical layers. In addition to the 2 sublayers in each encoder layer, the decoder inserts a third sublayer which performs multi-head attention over the output of the encoder stack. Similar to the encoder, they employ residual connections around each of the sublayers followed by layer normalization. They also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. This masking, combined with the fact that output embeddings are offset by one position, ensures that the predictions for position they can depend only on the known outputs at position less than I. Applications of attention. In the encoder-decoder attention layers, the queries come from the previous decoder layer and the memory keys and the values come from the output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence. This mimics the typical encoder-decoder attention mechanisms in sequence-to-sequence models such as. The encoder contains self-attention layers. In a self-attention layer, all of the keys, values, and queries come from the same place. In this case, the output of the previous layer is in the encoder. Each position in the encoder can attend to all positions in the previous layer of the encoder. Similarly, self-attention layers in the decoder allow each position in the decoder to attend to all the positions in the decoder up to including that position. They need to prevent leftward information flow in the decoder to prevent the auto-regressive property. They implement this inside the scale dot product attention by masking out all the values in the input of the sockmax which correspond to illegal content. Looking at the key contribution in this work, authors presented the transformer, the first sequence transduction model based entirely on attention, replacing the recurrent layers most commonly used in encoder-decoder architectures with multi-headed self-attention.